Not all numbers are easy to represent with, well, a fixed number of digits. When we're talking about, especially binary, in the machine, we're talking about we've got a fixed number of bits that we can handle. What if something gets out of range? And we do have an equivalent for this in decimal. Perhaps you recognize numbers like 3.0 times 10 to the 8th. That is, well, the speed of light in a vacuum. A lot of digits there. In fact, including the 3, if I were to write this out, there would be 9 digits, right? How about 6.02 times 10 to the 23rd? If anybody who's been in chemistry class probably recognizes that as Avogadro's number, right? Even worse than the speed of light, that's a 6 with 23 digits after that. That takes a lot of space on the paper, and so we use this thing called scientific notation in order to represent those values. Now, something I've left out of here are the plus signs, because these are both positive numbers. Now, there are some important things to recognize with these numbers when we're representing things in scientific notation. The first thing is we do have a sign, plus or minus, right? We also have a single decimal digit there. Now that single decimal digit is going to be 0 through, no, it's going to be 1 through 9, right? One single digit there, 1 through 9. So there are just those 9 possible patterns that you'll see in that single digit. Then you have a decimal point, and then the digits, the significant digits, are the fraction. So these bits are the fraction. And then times our base, and it gives us some sort of a power we're raising that to. All right, so what does this have to do with binary? Well, we are going to talk about something called IEEE, and IEEE stands for Institute of Electronics and Electrical Engineers. It is an organization that does many things, including standardizing certain ways or methods of, well, doing stuff in computing. And each one of these standards starts out with IEEE, and then a dash, and then the standard number. And the standard number we're going to be talking about today is IEEE Standard 754. And what this does is it gives us methods for representing floating point values in binary. And it does it for both 32 and 64 bits. If you program in Java, you probably recognize declaring variables as floats or doubles, right? Floats, doubles, using this standard. All right? So let's talk a little bit about that. But before we do, let's talk about just regular unsigned binary. Let's see, we have the number 10101011. So this is unsigned binary. Now, if we were to convert this, you would know that this 1 is the 128th place, right? This one right here, well, this is, well, let's just go ahead for a review. This is the 1, 2, 4, 8, 16, 32. That's the 32 position. This one right here is the 8 position. This one right here is the 2, and this one right here is the 1. You add all those together, 128 plus 32, that's 160, plus 8, 168, plus 2, 170, plus 1. This is equal to 171, all right? Now, if you recall from our discussion about unsigned binary, we had this ability to multiply and divide by powers of 2 by shifting this number left and right. Remember, if I take these bits, all the 1s in here, and move them 1 position to the left, what I'm doing is actually multiplying the number by 2. If I shift instead 2 positions to the left, that's 2 times 2, or 4. 3 positions to the left, that's 2 times 2 times 2, that's 8. If we shift to the right, we are dividing. And when we talked about this with unsigned binary, we talked about these 1s here kind of falling off the end into the bit bucket, so to speak. What happens, though, if there's actually a fixed point here? That fixed point, if we were to, for example, shift this so that, I don't know, let's shift it right 4-bit position. So I now have 1010.1011. All right. Now, that 1010.1011, that's a fixed point number. But now the positions mean something slightly different. Now, this point separates the positive powers, or the non-negative powers of 2, from the negative powers of 2. And if you recall, we've got, this is the 1's place, 2's place, 4's place, 8's place. So this becomes 8 plus that 1 right there is the 2's place plus, well, what happens on the right side of that point? The 0.1, this guy right here, that's 2 to the negative 1, 1/2, so that's 0.5, all right? The next one, this one right here, well, this is the 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, that's 1/8, that's 0.125. And then we have one more 1 here. This one right here is the 1/16th place, which is equal to 0.0625. All right. Now, what happens when we add all those together? Well, 8 plus 2, the only integer, whole integer values we've got there, 8 plus 2 is equal to 10. All right. But what's 0.5 plus 1.125 plus 0.0625? Well, it is starting on the right-hand side, so that's 5, and then we have 7, 8, and 6, right? Is that right? 6? Well, let's check. Okay, let's go ahead and take our calculator, and we will figure out what 171 divided by 16 is. Guess what it is? So it turns out that this mathematical ability to shift things left and right being equivalent to multiplication and division works with fixed point 2. Now, the problem is just like we had with those large values in decimal, what if we've got too many bits to represent? There is a solution, and it is in this IEEE-754 notation. So what if I've got, let's make a fairly large number. How about negative 101101010101.101? Okay. Now, that number, well, it could probably be represented with 32 bits in fixed point, but what we really want to do is not limit ourselves by the number of bits to limit where that point is going to be. So what we need to do is convert this to binary floating point. Now the way we do this is this. First of all, we use a multiplier, and remember, in our example here with the base 10, our multiplier was equal to the base. Well, our base 2 value here will now have a multiplier of 2. So what do we do to make sure to convert this number to scientific notation in binary? Well, what I want to do is I want to take out or divide this number by 2. Let's see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What I want to do is take out 11 2's. I got to make sure that I don't change the magnitude of the number though, so I've got to put them back in by having that multiplier there, right? All right, so we talked about the elements that make a fixed point value. What elements make a floating point decimal value? What elements make up a floating point binary value? Well, we have the sign, right? We have this integer here. That integer can be what? Well, it can't be 0, right? There's only one digit left in binary. It has to be a 1. And since it has to be a 1, guess what? We don't even need to remember it. We know that there's always going to be a 1 there. So that 1 we don't even need to remember. Then this portion right here, this is our fraction. All right. Oh, excuse me, I didn't write that far enough. That goes all the way over to there. All right. So all the digits to the right of this binary point, that makes up our fraction. And then we don't need to remember the base. We know we're in base 2, right? So this guy right here is the only other thing that we need to remember, and that's the exponent. So we only need to remember 3 things in order to store one of these floating point values on our machine. So how do we do that? Well, let's talk about it. In IEEE-754 floating point notation, we have 2 formats. We have floats and we have doubles. All right, now floats are 32-bit, doubles are 64-bit. All right, now all we're doing is we're taking 32 bits and partitioning those 32 bits up so that we can record each one of those values. And so let's see if my pen will give me my full, there we go. All right, so we have 1 bit right here. There is 1 bit. Because all we need in order to remember the sign is 1 bit. It's either positive or negative, 2 values. So 1 bit will do it for us. So we're going to label this guy S for the sign bit. All right. Now, the next thing that we're going to do, and by the way, this is really important because what we're doing is we're trying to compare 2 values. If we're trying to compare 2 values, what we want to do is put the most significant portion of the number, the thing that affects the magnitude of the number most, on the left side of this pattern of 1s and 0s. So what we're doing is we're going to put the exponent, because the exponent has a much greater effect on the magnitude than does the fraction, right? Because every time we multiply by a power of 2, we're actually shifting everything up to the next highest bit position, to the next highest power of 2. So the exponent is the next most important thing, and what we're going to do is we're going to do the next 8 bits in floating point, we are going to identify as the exponent e. All right. Now, do you remember from our discussion about biased or offset notation, why did we use bias or offset notation? Well, the reason we did was because it was really easy to compare 2 values, because the order in biased or offset notation is still from all 0s to all 1s. The all 0s representing the offset, the negative offset, and the all 1s representing the maximum value that all 1s are in unsigned binary minus the offset. Well, because biased or offset notation gives us a quick way to compare 2 values, we are actually going to use bias notation for our exponent. Specifically, in the case of 32, we are going to use bias 127. So in 32 bits, we are going to use bias 127. Now, how many bits are left over? Well, it turns out there are 23 bits left over. What are we going to put in there? Well, the only thing we got left to represent, and that's the fraction f. All right. Now, real quick, and we're not going to do for our examples or anything the 64-bit, because there's just not enough room on my limited light board here. But just to let you know that we do have a similar partitioning for 64 bits. Still dividing it up into 3 pieces, so we have our sign, exponent, and fraction. The difference is that instead, well, we still only need 1 bit for the sign. But since we've got some extra bits with the 64 bits, what we're going to do is use 11 bits to represent the exponent. And then we're going to use the remaining 53 bits for the fraction. But instead of this being bias 127, now it is going to be biased 1023. All right. So there is a slight difference, but really the principle is exactly the same. It really is simply just fill in the blank. Let me show you how easy it is for fill in the blank. First of all, this number right up here that we decided was negative 1 point and then the fraction times 2 to the 11th. Well, negative. All sign bits are going to be 1, and you can think of a line as a 1, right? A line as a minus sign. You have a 1 to represent negative numbers. So this sign bit being negative is going to put a 1 in that first or most significant bit position of our floating point value here. E. Well, E, this is probably the most complicated thing, but do remember that just to simply convert from bias 127 and convert a decimal number to bias 127, what we need to do is add 127 to our value, to what we're trying to convert. So 11 plus 127 is 138. All right? Now, 138 has a 1 in the 128 position, right? Pull 128 out of that, you got 10 left. So there's no 64, there's no 32, there's no 16, but there is an 8. Take 8 out of 10, you got 2 left, so there's no 4, but there is a 2, and there's no 0. So that pattern of 1s and 0s right there represents 11 in bias 127 notation. All right. So what goes in the remaining bits? Well, remember, we don't have to remember this integer position right here, this whole number, the 1 there. All we have to do is remember those bits. So starting to the right of this binary point, we simply copy down the 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, which hopefully got all the bits from the the point that's right immediately to the right of the binary point all the way into the end of the number. Now, that wasn't 23 digits. So what do we do with the rest of the bits? Well, we just pad it with zeros. Just put zeros. All right. And there you go. This number right here is, in fact, the IEEE 754 floating point value for 32 bits of this number that we put up here. All right. So what about going the other way? What if we opened up memory and we found a value, 32-bit value? We know it's supposed to be floating point. Somebody's declared it as floating point. What pattern of 1s and 0s that we found, what does that make in floating point binary? Well, let's come up with something. How about 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0. We'll just put a whole bunch of zeros, right? Now, to convert this to floating point binary, it's just fill in the blank. Specifically, it is fill in the blank with this format. It is plus or minus 1 point f times 2 to the e minus 127. All right. It's just fill in the blank. We need to find the sign in this bit. Then we need to find the unsigned, and this, by the way, this minus 127 is taking care of the bias notation for us. So we need to find out what E is. Then we need to figure out what F is. We just simply take the pieces and insert them into this formula. So let's partition our number. So there's the sign bit. 0 means positive, so we know that it's a positive number. By default, you simply put a 1 point right after it. Then you look at the next 1, 2, 3, 4, 5, 6, 7, 8 bits. This is our E. And so E is equal to 128. Looks like I made exactly the same E. Didn't mean to do that. Sorry. This is 128 plus 8. That's 136 plus 2 is 138. So 138 minus 127. So this guy right here is going to be 11. And then the remaining bits, that is our fraction. This is F. So we just copy those bits directly, and I'm not going to copy all these trailing zeros. Let's just copy the bit positions all the way until we get to the rightmost one. So this is 0, 1, 1, 0, 1 times 2 to this 11. All right? And there you go. All right? Now, you may have noticed that we can't represent 0. How do you represent 0? Well, the way we represent 0 is that we make, well, E equal to 0 and F equal to 0. By making E equal to 0, that gives us an offset, or the biased 127 value of E equal to negative, our exponent is going to be negative 127. Very, very small as we can get. So the smallest possible value we can get is all zeros for E and all zeros for F. That would be 0. The sign bit, ignored. All right? Now, what about infinity? Hey, we've got all these bits. Why don't we go ahead and represent infinity? One of the things that we do for infinity is, well, we make E as large as possible, all ones, right? And if we make all ones there, then this becomes 255 minus 127, which is 128, the largest possible value. And while it's nowhere near close to infinity, it's close enough so that we can assume that it is infinity. If the F, the fraction, is set to all zeros, that is officially what we're calling infinity. If F is a non-zero value, we get something called not a number, NaN. You may have been familiar with it. You may have had experience with this, but basically what it's saying is whatever we came up with, the result is not really a number. So E of all ones, F of all zeros, plus or minus infinity. E of all ones, F of a non-zero value, not a number. All right? So that should be enough information to go ahead and get us started in understanding IEEE 754 notation.